Okay, in this video we're going to look at Newton's laws, but this time we're going to take a look at it in terms of rotational motion instead of linear motion or translational motion. You will see that in many problems we can solve using the law of rotational motion, the first law of rotational motion, without really thinking about translational motion. But as we get to the more complex problems, it is going to be very helpful to just remember what does the first law say for translational motion. What I've tried to do is to simplify these down. So instead of using like the wordy way that Newton might have expressed it, I'm trying to give you a little more simplistic, a more clear and concise explanation of what the first law is. And the first law simply says that objects travel at a constant velocity when the net force is zero. Okay, if the net force is not zero, then they don't travel with constant velocity, and then you're going to see some form of acceleration. That could be linear acceleration or centripetal acceleration. But in this case, what it's saying is that if the net force, and we would calculate the net force by simply adding up all of the individual forces, and there could be 3 or 4 or more, that would be equal to 0. So when I add up all the forces and they add up to 0, then that means that the acceleration will be equal to 0. We will not have any acceleration. We will travel with constant velocity. Now that could mean that we're at rest, that we're just simply staying at rest, or that we're traveling at a constant velocity. So on the highway, it may not seem obvious to everyone, but if you've studied physics, then you should understand at this point that cars traveling at a constant velocity are doing so because there is no net force acting on them. That's not to say there's no forces acting on them. Of course, there are forces. There's thrust, there's drag, there's internal friction. But if we were to add all those forces up, they would add up to 0. That is why the object is not accelerating. Now, in rotational motion, we don't look only at the forces. What we look at instead is the torque. And what the first law would say about rotational motion is the same thing it says about translational motion, and that is that objects will rotate with a constant angular velocity if the net torque is 0, right? So remember, force is what causes linear acceleration. What causes rotational acceleration is torque. And so what they're saying is that if I add up all the individual torques, however many that there happen to be, and if those torques add up to 0, then we will again get 0 acceleration, but this time not linear acceleration. This time we'll be talking about angular acceleration. The angular acceleration will be 0 so long as all the torques cancel out. Now that would apply to things, for example, that were stationary. So anything that is stationary, you could say that there is no net torque because the thing is not rotating, or it has no rotational acceleration, or it could even be moving. So for example, a turntable, when a turntable is spinning, the total torque on that turntable is 0. The motor is simply turning at a rate that matches the friction, and as a result, the object rotates at a constant angular velocity. Now, I would say that there are 3 kinds of problems, right? So with torque, there's just the simple torque problems, which we looked at in the previous video, where you just calculate the torque by itself individually by looking at the force and the lever arm and the angle between them. Then there is what I would refer to as the seesaw problem, and that's what we're going to look at first. And then finally, there are the most complex problems in which we actually will need to take advantage of both of these, or at the very least, it would be very wise of us to take advantage of both rotational and translational motion, because these 2 things are what causes stability. So stability in a static situation means that simply nothing is changing. And in order for nothing to change from what it's doing, for the object to continue moving in the way that it's moving, both the net force and the net torque must be 0. Okay, so let's apply this to a specific problem. And we're going to start with the seesaw problem, the idea of the seesaw problem. The idea with the seesaw problem is essentially that there are only 2 forces. So the 2 forces are going to be the person sitting on either side of the teeter-totter. So let me go ahead and draw a picture of the seesaw. It's not super common to see the seesaws so much anymore on the playground. But certainly when I was younger, they were very common. Sorry. Make this a little bit longer. So make sure that they're the same length on both sides. On one side, we're going to sit a person. Okay, and just so it's clear, we're always going to put the smallest person at the furthest possible point. And then the question is, since this person is exerting a force in the downward direction, which we're going to call F1, the heavier person, if they sit on the end over here, right, with identical forces, the person who exerts the most torque is the person who has either the greatest force or greatest lever arm. So if they are both sitting the same distance from the pivot point, this is the pivot point, then the heavier person is going to exert more torque, of course, because F times R will always be more for the heavier person. So what needs to happen is we need to come in a little bit, and we're going to put a heavier force. The heavier child is going to have to move in a little bit. And the reason for that is because if you put the heavier child at the end, then that person is going to always exert more torque, and this smaller person over here, they're probably never even going to touch the ground. I mean, they're just going to be up there all the time. The person on this side could push up, and that will reduce the torque on their side. But as soon as they stop pushing, then they will fall right back down. So it's not a very fun ride unless you get this thing balanced. We want the torques to be balanced, and that way just a slight push by anybody will make the thing start to rotate in that direction. So the question is, how far away does this person need to be? Now, obviously, if the board is 8 meters long, then that means that we have a lever arm on one side, which is equal to 4.0 meters. The question is, what is the R on this side, right? How small is the R on the other side in order to make sure that this thing is going to balance properly? Okay, so the basic idea, let me return back up to here. The basic idea is that all the torques add up to 0. But in this case, there are only 2 torques, torque 1 and torque 2. So it must be that torque 1 and torque 2 are equal to each other, equal but opposite, in order to produce this balanced situation. We want the 2 torques to balance. In any situation where the torques are balanced, then the object is either going to stay static, meaning that it's not moving at all, or it's going to just continue to rotate at a constant angular velocity. So in this case, F1 times R1 would be equal to F2 times R2. I don't need to worry about the angle right now, because even if the angle was there, even if this was tilted a little bit, the angle would be the same on both sides. Or at least it would be the supplemental angle, so that we would end up getting the same sine value. But in this case, the forces are being applied perpendicular to the seesaw, so it's really not relevant, the angle. We can leave that portion out. It is important where the force is coming from. So in this case, it's coming from M1 times G times R1 is equal to M2 times G times R2, right? So obviously in this case, we don't need to worry about gravity. Now you can plug it in. There's nothing wrong with you plugging it in, but we don't need to have it. It's on both sides. I can divide the left side by gravity. I can divide the right side by gravity. And in the end, I will end up with this expression that R2 is simply equal to M1 times R1 divided by M2. So that would be, in this particular case, 45 times 4, and that would be divided by 60, so that we get an R2 equal to 3.0 meters. Now, that hopefully is not surprising that this R is 3/4 of the other person's R, because this person's mass is 3/4 of this person's mass. So let's just take this point right here, and let's just come back up here and just see how that would have played out. That says M1 R1 is equal to M2 R2. It's very common for them to ask you, things like, for example, what would be the ratio of their lever arms? What's the ratio of their masses? Based on, if you know the lever arms, then you can get the ratio of these objects. So in this case, it would be M1 divided by M2. I'm dividing by M2 on both sides. That moves the M2 over here. And then I'm going to divide by R1, and you will see that they are inverses of each other. So the ratio of the masses is the inverse of the ratio of the lever arms, or vice versa. So it's not a surprise that the 3 divided by 4, that ratio is there, because that is the ratio of their masses. The ratio of the masses is going to determine the ratio of their lever arms. It has to be the same in order for you to have that balance. One thing that we ignored was the mass of the board. In fact, I did not even tell you what the mass of the board is, but I did not tell you because I was supporting the board at its center of mass. And that's a really important thing. So if you apply a force to an object at its center of mass, then it won't rotate. That's not going to cause rotation if that is the only force. So this idea of center of mass it's kind of an important concept. I don't want to spend a lot of time talking about it, but ultimately extended objects like, let's say, for example, the 2 people in the last problem, Extended objects can be treated as point particles. That is to say that all of their mass is located at their lever, at their distance of their lever arm. And what that means to be a point particle is with all of the mass at that point. Okay, so returning back to the seesaw problem, of course there is a force being exerted by this support piece pushing up against the bottom of the board, and then also there's the weight of the board, but those two forces are being applied at their center of mass, and so as a result there's no distance between the pivot point and that force, and if there's no R, which there is no R for this one, then there is no torque as a result of that. That's an important aspect because it turns out that you can pick any point to use as your point of rotation, but there are smart choices and there are not so smart choices. You can make your life a little bit easier, or you can make your life a little bit more difficult. So this seesaw problem is probably the most likely thing you're going to see. You're going to get two torques balancing each other. This would be true, like let's say you're pedaling on your bike. So your pedal you apply a force with your foot to produce one torque. The chain is applying a torque in the opposite direction. And as a result, in order for you to achieve an angular velocity which is not changing, you would have to balance those two torques. So let's take a look at the most complicated problem. This is actually for the topic of rotational motion. This is probably one of the most difficult problems that you're going to be asked to look at. And in order to sort of create a slightly more complex or more challenging problem, we're going to have to think about the direction. Okay, so in terms of the direction, when we actually have objects that are rotating, we do have to think about what that means, because in the past, we applied directions to be up or down, left or right, east, west, north, south. Those were easy because they kind of line up with the natural coordinate system that we use. But now we're using a rotational coordinate system. So that means that we can't use the same old notation that we're using before. So let's say, for example, that we had a metal rod that was swinging around. Okay, so this thing can rotate either in the counterclockwise direction or it can rotate in the clockwise direction. This is what I would suggest doing. I would call anything that rotates in the clockwise direction, I would call that positive. Anything that rotates in the counterclockwise direction, I would call that negative. Okay, this is a very simple system. We only keep track of two directions. Things are either rotating in the clockwise directions or things are rotating in the counterclockwise direction. Always viewed from the same direction. So I wouldn't view one from this side and then try to view other forces or other torques that are being applied from the other side, looking at it from underneath the piece of paper. Always want to view it from the same direction. So one of the really good examples where you can see this idea of torque and then also the translational motion being used to solve a problem is if you have somebody like a construction worker who might be trying to work at an elevated position. And so one of the things that they'll do is that they will put sawhorses. I'm going to draw a picture of what this would look like. So we have a long board. The board in this case is 5 meters long. And we have a person who is standing, right? So a construction worker who is 85 kilograms, is standing on a 35 kilogram wooden plank supported by two sawhorses. The two sawhorses are 0.5 meters from the ends. So 0.5 meters from the ends means something like this. So a sawhorse is essentially some wooden boards that create sort of an A frame. And then you can set the boards on it, and then the person can stand up here. Now we need to put the person in the correct place. It says the construction worker is standing 1 meter from the end of the board. Okay, so in this case, it doesn't matter which end that we put this in. This is 0.5 meters right here. So that's 0.5 meters to there. On this side, the person is standing 1 meter from the end. So there's the person. And then there's one more thing to think about, and that is the board itself. So this board is experiencing 4 forces. One is the weight of this person pushing down on it. 2 is this sawhorse pushing up, which we're going to call sawhorse B. And then the second one is this sawhorse here. We're going to call that sawhorse A. That's 3 forces, and then the last force is coming from the center of mass. So remember, for extended objects, we're going to treat them as though they are point particles located entirely at that center of mass. That's a little bit of a simplification, but it works out perfectly accurately. It turns out that while that is a kind of a simplification that we're using, it's a completely valid simplification for us to use. Okay, so first step now is we have a picture of what it looks like, but it would be very helpful to have a diagram that is more simplistic, that's easier to follow. And so what I'm going to do is I'm going to redraw the board, but I'm going to draw it just simply as a line. Okay, and there are 4 forces. So one is the weight. I'm going to put that right at the middle. It's a relatively small arrow. I'm going to call that F1. That's the force that the weight of the board is exerting essentially on itself. And then 1 meter away, and let's put that distance on there. So the distance between here, you know what? Let's wait. Let's just put the forces in their correct locations. So at a half a meter away from the ends, so pretty close to the ends, maybe something like this, there is force A that comes from sawhorse A, and then there's force B at about the same distance but on the other side. That's a longer arrow. Okay, and the reason why I know that arrow is longer is because the person is standing closer to sawhorse B. So sawhorse B is taking more of the weight than sawhorse A is taking. And the last thing then is the person. The person is in here. I'm going to call them F2. They are the 2 downward forces, one from the weight of the board, one from the weight of the person, and then the 2 upward forces, which is the the force from the right sawhorse and the force from the left sawhorse. Okay, so at this point, I don't need to establish. I have not established what is my point of rotation. But this is a really important aspect of the first law for rotational motion. You can pick anywhere. You can pick anywhere. It's different than when you're looking at the first law for translational motion. First law for translational motion, there's one equation. That's it. All these forces have to be in there, and we can write that equation. That says that the net force would be equal to F of A plus F of B, they point upward, minus F1 minus F2, those must be equal to 0. But that's it. There is only one net force equation, and unfortunately, there are 2 unknowns. I don't know A, and I do not know what B is right now. So that leaves FA and FB to solve for, but with only one equation. So obviously, we need to have a second equation. And where we're going to get that second equation is from the torque. So while there is no acceleration of this object, there's also no rotational motion of this object. Now the problem, or I would say it's both good and bad, is that you can pick the point of rotation when there is no rotation. You could pick any point. I could, for example, pick this point right here at the end of the board and say that this is the point at which it is rotating around. There is no torque around this point because it's not rotating around this point. But I could also say here, I could pick here, I could pick anywhere along the board. In fact, this equation is so powerful, I could pick any point. It doesn't even have to be on the board. I could pick a point like Midway Airport, or Dallas, or the planet Saturn, or I could pick anywhere. This object is not rotating. Therefore, any point of rotation that I choose, there will be no torque around it. Okay, so there's literally an infinite number of torque equations that will satisfy what this is saying. However, there are better choices that you can make. And right now, the best choice that you could make would be as if we could eliminate one of the unknowns. And how would we eliminate one of the unknowns? We would choose it as the point of rotation. Now, I could have picked either A or B. But by choosing that to be the point of rotation, that is going to allow me to work out the lever arms now, but more importantly, it's going to eliminate this force from the torque equation. So because there is no R for this force, because I'm choosing the point of rotation to be right here at that point, therefore, there's no torque produced by it. So when I look at the net torque equation, this is going to be my second equation. So now before we do this, let's work out the lever arms. Now that we've chosen where the point of rotation is, let's just work out how far are each of the other 3 forces. So remember that A and B are a half a meter in from both sides. So as a result, we're going to end up with a lever arm here, which is equal to 4 meters. I'm going to subtract out the half meter from the right, half meter on the left. That leaves me 4 meters, so that's the distance between those two. Remember that F1 is the center of mass of the board, and since that's going to be 2.5 meters from the end, but it's a half meter to here, that means that the R for this one is going to be 2.0 meters. I am 1 meter away from this side. I'm a half a meter away from this side, so that's 1.5 meters subtracted from 5. That leaves me with 3.5 meters for the lever arm. Okay, so I have my RB, the radius for the lever arm for force B. I have R1, which is the lever arm for the center of mass of the board, and I have R2, which is the lever arm for the force that the person is exerting, by standing over there on the edge. So let's go ahead and put these into the equation, and let's see how this is going to work out in the end. So I'm going to go ahead and start putting all of the positive torques first. So in this particular case, just take a look what's going to happen. This force is going to cause this to rotate in the clockwise direction. The force number 2 also in the clockwise direction. But force B, that is going to cause this guy to rotate in the counterclockwise direction. The torque being applied by B is going to cause counterclockwise rotation. So I'm going to list him last, since, as we said, we're going to use the counterclockwise direction as the negative direction. So what I would find is that F1 times R1 plus F2 times R2, my two positive torques, minus F of B times RB, that must be equal to 0. Now, what's really especially powerful about this particular equation is the fact that I've already eliminated one of the forces. So normally what would happen is I would have to do a addition or subtraction of the equations, or do some kind of substitution or something like that. But the great thing about the torque equation, because you get to choose your point of rotation, is you can actually use that as a way to eliminate one of the unknown forces. So now I can actually solve this equation. I actually know everything in this equation except that I don't know what the force for B is. So I'm going to go ahead and make one step here, and that says that F1 times R1 plus F2 times R2 would be equal to F of B times RB. Okay, and at this point now I'm going to go ahead and start throwing the numbers in. So the force for number 1 is going to be 35 times 10, and then times that lever arm, which is 2. The second force is 85 times 10 multiplied by 3.5. You know, one thing I feel like is important to notice is I'm not taking out, I can't cancel out gravity, because this force is not based on gravity. It's just a force. It's not calculated by using the weight of anything. So I have to put in the 10 because I need these to be forces, whereas in the previous problem, since both of the forces were based on weight, I could go ahead and get rid of the gravity. I didn't need to have gravity. I could just cancel it out. But in this instance, I won't be able to cancel out gravity. So I'm going to leave F of B, and then my lever arm for this guy is 4. So this ends up being 700 plus, when you multiply 85 times 10 times 3.5, that's going to be 2975. And that's going to be equal to 4 times F of B. When we bring those two guys together, they will come together to be 3675. And then we'll divide by 4. And when I divide by 4, I end up with 919 newtons. That is my force for B. Okay, now you have a couple of options, about how you can go for F of A. Now we could create a new torque equation. We could say, well, let me make F of B. Let me make this guy the point of rotation, and I'll create a new torque equation. But that would be kind of a stupid move, because I already have an equation that says that these two forces added together minus these two forces will be equal to 0, and now I have 3 of the forces. This is just a subtraction problem. I don't need to create anything new. I've already created the first equation that I needed, but now I'm going to go ahead and use that equation, which says that F of A plus 919 minus 350, that's the weight of the first person. That's F1 is the weight, the force from the first guy, minus 850. That all must be equal to 0. Okay, so here's my equation. the force of A plus the force of B minus the force from the weight of the board minus the weight of the person must all add up to 0 because the object's not accelerating. And so therefore F of A would be equal to 281 newtons. So that's typically how the problem is always going to end. The problem will always end with you going back to the linear motion, the net force for translational motion, and it's using that because that's just a subtraction, addition and subtraction problem to finish the final forces. If you had more forces, still at the end you would finish with this one. If I had one more force or like an unknown person or something like that, and I need to find another force, I would still use the same technique, and I would still end with the final force I would find by just adding all the other ones that I've already figured out, and then just using addition and subtraction to find that final force.